There are two things I would like to talk about today. The second one is the set of rotational kinematic equations. This is a set of equations that lets us describe rotational motion when the angular acceleration is constant. But before we do that, I would like to talk about the set of expressions that relate rotational motion to translational motion. A good place to start there is with what's called rolling without slipping. Rolling without slipping. That is the rolling motion of a wheel or a tire or a ball or whatever it is that's not like this, where it slips on the surface, but like this, where it rolls without slipping on the surface. There are relations between the translational motion and the rotational motion. Let me draw a surface with a wheel that is rolling along it without slipping. So there's the center, here's the wheel, and this wheel has some radius r, and it's turning this way so that as it rotates, it's going to move sideways to the right. Let's suppose that this wheel rotates through some angle that I'll indicate here. As it does, on the rim of the wheel, we trace out an arc that I'll draw in red that looks like this. And that arc has a length s, so that if this wheel rolls without slipping, the wheel will move sideways the same distance s. The wheel is going to end up over here, right above this point. Let me draw the wheel in a very light color so that it doesn't get in the way too much. The wheel ends up right there. It's moved sideways the same distance s as the arc length traced out by a point on the rim of the wheel. What we want to do here is come up with a set of expressions that relates this rotational motion to the translational motion. The way we start is by writing down the arc length equation, s equals r times theta. Now suppose I take the time derivative of this equation. ds dt equals r times d theta dt. That ds dt on the left-hand side is the rate at which the arc length is changing. That's also going to be the rate at which this line is getting longer. It's the rate at which the wheel is moving sideways. It's the magnitude of the wheel's instantaneous velocity. That's v. And that's going to equal r times d theta dt, which is r times omega. So the sideways velocity of this wheel is going to equal r times omega. The bigger the wheel is, or the faster it's spinning, the faster it's going to be moving sideways. So v equals r omega. The translational velocity of a wheel that's rolling without slipping depends on two things: how large the wheel is and how fast the wheel is rotating. Suppose we take another derivative so that the time derivative of velocity becomes the acceleration. Now we're talking about whether the wheel is speeding up or slowing down in its translational motion. That's going to equal r times the time derivative of omega, which is alpha. So the acceleration of this wheel sideways equals r times alpha. If the wheel is spinning up or spinning down, if it's spinning faster or slower as time goes by, it will be accelerating sideways as well. It'll either be speeding up or slowing down in its sideways motion. So these are the equations that relate translational motion to rotational motion for rolling without slipping. Let's consider one more thing before we write down the rotational kinematic equations. Suppose we have a wheel that's not rolling without slipping, but it is just rotating. So it's fixed on some axle and the wheel's rotating. It has a radius r, and we'll assume again that it's rotating this way. like it was above. I want to talk about the components of velocity and acceleration for points on this rotating object. When you have rotational motion like this, the natural coordinate system is in the tangential and radial direction. So let's consider this point here. The tangential direction looks like this, and the radial direction is this way. So that as this wheel rotates and we come around here, for instance, the tangential direction would be here, and the radial direction would be here. What I want us to think about are the components of velocity in the tangential and radial directions, and then do the same thing for the components of acceleration. I would like us to get Vt, the tangential component of velocity, and Vr, the radial component of velocity, and then tangential component of acceleration, and radial component of acceleration. Let's do the tangential component of velocity first. That's this component that I'll trace out in orange here. We should be able to see that this orange component of velocity is going to be exactly this up here. However fast the wheel was moving sideways when it was rolling without slipping is exactly how fast a point on the rim was moving in the tangential direction. So just like we described above for rolling without slipping, the tangential component of velocity equals r times omega, the magnitude of the angular velocity. The farther from the axis of rotation, or the faster the wheel is rotating, the faster it will be moving in the tangential direction. Suppose I consider the motion of a point closer to the axis, right here. Then the tangential velocity is going to be smaller because it's going to trace out less distance in the same amount of time. In one period, one time it takes this wheel to go around, this point out here traces out this large circle. It covers a relatively large number of meters in those number of seconds. But this one here has the same period, but in that amount of time, it traces out a smaller distance. So because r is smaller, the velocity is going to be smaller, even though omega is the same. All points on this wheel have the same omega. The farther away they are from the axis, the larger distance they trace out per unit time, so the larger magnitude of velocity they have in the tangential direction. The tangential component of velocity has a magnitude that depends on two things: how far it is from the axis and how fast the object is rotating. Vt equals r omega. Now for something that's rotating in circular motion, all of the velocity is in the tangential direction, and points on the object aren't moving towards or away from the axle at all, so the radial component of velocity is 0. For the accelerations, we can go through a similar argument as above to get the tangential acceleration. The tangential velocity was r times omega. To find the acceleration in that same direction, we just take its time derivative. The time derivative of this expression tells me that the tangential acceleration equals r times alpha. If you want to know whether this orange component is getting longer or shorter, if a point on the rim is moving faster or more slowly in the tangential direction, you need to know whether the object is rotating faster or slower. If it's rotating faster as time goes by, the tangential acceleration will be such that this orange vector will be getting longer. If this is negative, so that it's rotating more slowly, the tangential acceleration will be negative, and this orange vector would be getting shorter as time goes by. The radial acceleration we've already talked about. We know that is v squared over r. For something moving in circular motion, the speed v is just the magnitude of the tangential component, so we can substitute r omega into here, and if we want, we can write this as r squared omega squared over r, which is r omega squared. So the radial acceleration we can write two ways. We can write it as we used to, v squared over r, or we can write it as r omega squared. And its direction, of course, is to the center, just like it was before. The radial acceleration of anything in circular motion is toward the center. Those are the expressions that relate rotational motion to translational motion. We have the case of rolling without slipping, and then we have the tangential and radial components of velocity and acceleration. Let's look next at the 4 rotational kinematic equations. I'm going to erase this, and I'm going to write down the kinematic equations that we had for translational motion. And then we'll talk about the same things for rotational motion. When it came to translational motion, we had these expressions. I'll write them down for the x component. Which apply only if the acceleration in that direction is constant. So if we have constant acceleration in the x direction, these 4 equations will tell us about the displacement, the velocity, and the acceleration. The way we got these equations, if you remember, is we started with the kinematic definitions, and we performed algebra on them. There was not actually any physics involved. All we did was manipulate those equations under the assumption that the acceleration was constant. Now, because those derivations were done just using algebra, we can imagine we do the exact same algebra on our rotational kinematic definitions, and because those definitions have the same algebraic form as the translational ones, we'll end up with exactly the same expressions, just in our rotational variables instead of the translational ones. So that instead of velocity v, we'll end up with omega, and instead of acceleration a, we end up with alpha. Instead of the displacement delta x, we'll end up with the angular displacement, and again here and the time independent equation. Which will apply if the angular acceleration is constant. So again, what we did to obtain these equations was to take the kinematic definitions, perform algebra on them, and solve for various unknowns. Because we have the same form of the definitions, we can perform the exact same steps of algebra and end up with the same results, just with different letters and, of course, different meanings attached to them. This set of 4 rotational kinematic equations can be used in exactly the same way as the translational kinematic equations were way back in the beginning of this course. So the thing to do is to look at some examples and problems and get some practice using these. So we'll do that next.